Alright guys, today we're going to be talking about Hess's Law. So, the formal definition of Hess's Law is as follows. If a reaction is carried out in a series of steps, delta H, or the enthalpy change, for the overall reaction will equal the sum of the enthalpy changes for the individual parts. So, a little bit of background information about delta H, our enthalpy change. Enthalpy change is a state function, so this means it only depends on the amount of matter that undergoes change, and the initial state of the reactants and the final state of the products. Therefore, it doesn't matter by what means you go from reactants to products, it just means that you have to consider how much is being involved in your equation and the state of your reactants and the state of your products. So, this means whether a reaction is carried out in one step or in a series of steps, which it often does. You may not be able to tell on paper because it just looks like one step, but it's actually a multi-step process. Anyways, so whether it's one step or a series of steps, the sum of the enthalpy changes associated with the individual steps must be the same as the enthalpy change associated with the one-step process. Okay. So why is this important? Well, Hess's Law is important because it saves us from making calorimetric measurements for all reactions. As a chemistry student, this is really, really important because we can use step reactions to find the overall delta H for any equation. So, and if we have an equation on paper that we haven't necessarily found the change in enthalpy of, but we have found the change in enthalpy for the steps that make up that reaction, we can use the enthalpy changes from each of those steps to find the delta H in the equation that we not necessarily have determined experimentally, and we won't even have to do an experiment, which is awesome. So, a little better visual representation of Hess's Law. Let's say we have methane gas and 2 moles of oxygen gas in our reactants, and we are trying to form carbon dioxide gas plus 2 moles of liquid water. We're trying to find the enthalpy change involved in that reaction. Well, in reality, going from these reactants to these products, it's a two-step process. So, the first step involves going from methane gas and 2 moles of oxygen gas and forming carbon dioxide gas and 2 moles of gaseous water. That process requires negative 802 kilojoules. The second step, going from carbon dioxide gas plus 2 moles of water in its gaseous form to carbon dioxide gas and 2 moles of water in its liquid form, requires negative 88 kilojoules. So, to determine the overall change in enthalpy for that whole reaction, we can add up these two values, which would give us negative 890 kilojoules, without ever having to actually conduct this experiment. So this is what a typical Hess's Law problem may look like. We have a 3-step equation, and this is the final equation that we are trying to find. So, the first thing to do when approaching a Hess's Law problem is to make sure that reactants and products are on their appropriate sides. We have carbon as a reactant, hydrogen as another reactant, but ethine as a gas is actually a product. Unfortunately, in our step up here, it's a reactant, so this means we have to flip this equation. So what does this mean for our change in enthalpy? Whenever you flip an equation, you also have to flip the sign. So this was originally a negative. This originally had a negative delta H value, but it is now positive. Okay, so now we have ethine gas on the side that needs to be. Awesome. The next thing that we should notice is that we have 2 moles of solid carbon down here, but only 1 up here. That's a problem. So, in order to get the appropriate, or to have the appropriate number of moles, we have to multiply this entire equation by a factor of 2 in order to get 2 moles of carbon like we have in our final reaction. So, when you multiply an equation, a step in an equation by a coefficient, you also have to multiply the delta H value by that same coefficient. This is an important rule to remember when working with Hess's Law problems. So now we're in the final steps of this problem. We have the appropriate number of moles of carbon. Our hydrogen is on our reactant side, which means, and it's also the appropriate number of moles, so we don't have to manipulate this third step at all. And ethine is on the product side. Yes. So, the next step is kind of fun, and you have to think a little bit like a math student for this last part. So when you think about an algebraic equation, in order, when you have the same things on both sides, you're allowed to cancel. Same applies here. We have 2 moles of carbon dioxide gas on the reactants and 2 moles of carbon dioxide gas in the products. So those can go bye-bye. We also have 1 mole of liquid water here in our reactant side and 1 mole of liquid water on our product side. So those both can cancel. The last thing to go is our oxygen. Now this is a little tricky for you people with difficulties with fractions. I have that. But you see you have 5/2 moles of oxygen here, and you have 2 moles of oxygen here plus 1/2 mole of oxygen here, which actually adds up to be 5/2 moles of oxygen. So your oxygen on the reactant side and oxygen on product side all cancel. Now we're left with everything that we need to form our final reaction. We have 2 moles of carbon, 1 mole of hydrogen gas, and 1 mole of ethane gas. Yippee! So, last thing to do, add it all through. So you bring all of your reactants and your products down, and the last step is to add all of these values together. So you add positive 1,299.6 kilojoules with negative 787 kilojoules with negative 285.8 kilojoules, and that gives you 226.8 kilojoules for this overall reaction. Woohoo! Congrats on your first completed Hess's Law problem.